Hey everybody, good morning. This is Mr. Ainsworth. We're going to get into Chapter 2, Section 1 on what's called the limit definition of the derivative. Okay, the limit definition of the derivative. There are many derivative rules in differential calculus, and they're all based upon what's called the limit definition. And that's why in Chapter 1 we talked all about limits, because we're going to need all our techniques from last chapter. All right, the first thing we need to do is that if we're given a function, let's say y equals f of x, where f of x is any function, the geometric meaning of the derivative now, okay, of y or of f of x, which is called either y prime, the derivative I'm talking about here is called y prime, or f prime of x. Again, this notation here is called prime notation. It's a short way to write the derivative of y in respect to x, which is written dy dx. Okay? The derivative of y in respect to x. We have three different ways to write the first derivative. Y prime, f prime of x, and dy dx, or the derivative of y in respect to x. The geometric meaning of the derivative is the slope of the tangent line at any point P. The slope, okay, underline slope, of tangent line at any point P. At any point, let's say P. All right, so let's take a look at how we can develop this idea so we can apply it, because in applications, the derivative is very, very useful. Okay, so what I'm going to do is I'm going to take a look at a function here. And there's f of x right here. It could represent any function. And I'm going to place P on the graph. Let's place P right here. P can be anywhere. I said any point P, which means P could be at any point on the x or on the function. And let's figure out how we're going to get the slope of the tangent line at point P. Now let me approximate the tangent line first. I'm going to put that in blue. Well, actually red. That's our target. Okay. And in this case, the tangent line, intersects the curve at one point. In this case, point P. So our approximate tangent line would be here at point P. Now it would change if P was up here. If P was up here, the tangent line would be much, much steeper. But in this case, the tangent line at point P would look like this. It's the tangent line. It intersects the curve once. So the question is, how do you find the slope of it? Okay, the slope of the tangent line at that point. Well, what we do is we use another point, and we use basically algebra 1 and the concept of slope that you know already. All right, so what I need to do now is pick another point on the curve. Let's call it Q. Okay, and we use the slope of the secant line, which we can calculate, because if we're given point P and we're given point Q, we can calculate the slope between those 2 points because we know the definition of slope. Now the secant line through P and Q looks like this. Let me draw that. Okay, so it looks like it has to run through P and it has to run through Q. So let's approximate the slope of the secant line, or approximate the secant line. Trying to get it right through P and Q here. That's approximately. Okay, this is called a secant line because it runs through the curve twice. Okay, intersects twice. And thus we call it a secant line. You know that from geometry a couple years ago. You know that from geometry the tangent line intersects the circle once and the secant line intersects twice. That's why we call the red line a tangent line and the blue line a secant line. Okay? The question is, how do you get the slope of the secant line to approach the slope of the tangent line? Because the tangent line, or the slope of the tangent line, is what we want. Now we can use the slope of the secant line to approximate it, but as you can tell in this picture, it's not a very good approximation. It's much steeper. I mean, the slope of the tangent line is almost zero in this case, although it's not always zero. It depends on where point P is, like I said. That's just an example. So how do you get the slope of the secant line to approximate better the slope of the tangent line? Okay? And the answer is pretty simple. What you want to do is slide Q down here along X and place it closer to P. Let me do that. Let's place. Let me switch to green now, and place Q here. And let's call this one Q1, and let's call this one Q2, so we can differentiate the Qs. The second secant line through Q2 would look like this. Okay, so let's draw that. It has to run through P and Q2, so it would be approximately here. Okay, it's not exact, but it's getting better. Okay, and this is another secant line. That's another secant, call it PQ2. All right. The one in blue, this one's called PQ1, of course. All right, you define a line by 2 points on the line. And so you can tell that the slope of the secant, the second secant line here, is getting closer to the slope of the tangent line because it's getting more shallow. It's approaching the slope of 0, which the tangent line looks like it has. Okay, in this case. So what we want to do is get Q really close to P so that the slope of the secant line gets closer to the slope of the tangent line. All right, let me show you that a little bit better here on another program called the Geometry Sketchpad. All right, now here's P. Now let's suppose we want this, the slope of the tangent line at P. Now the slope of the line that we're dealing with right now is a secant line because I have it running through P and Q. But if I slide Q down here towards P, and if I get Q infinitely close to P, it becomes a tangent line. And notice it intersects at only P, which means that it's a tangent line. And if we can find the slope of that line, then we've achieved our goal. All right, so what we need to do is approximate the slope of the tangent line, or get the slope of the tangent line, by sliding Q infinitely close to P. Notice I said infinitely close. And you can do that in calculus because we know about limits. We can take the distance between these points and let it approach 0 and make our goal happen. Okay, that's what we're going to do. We're going to slide P or Q infinitely close to P and then find the limit, and that limit would become the slope of the tangent line at that point. All right. Okay, so let's define a few more things here to make things a little bit more specific. Okay, now let's take a look at Q1. Go back to there. And let's define its position a little bit here. And this position on the x-axis. Now the distance between the 2 points, between x and this point here, well, let's give it a name. We're going to call this distance delta x. And because it's delta x, where delta x is some positive number, it could be 4 units, it could be 1 unit, it could be half a unit, it could be anything. Okay, it's just a variable here called delta x. To get the point on the x-axis where Q1 lies, you just have to simply add. You take x plus delta x and you get this position right here, which is x plus delta x, whatever that is. Okay, now to calculate slope, you need their y values, and we need the positions of these points. So if our function is called f of x, then at P here, P has coordinates x, comma, well, it's called f of x. All right, you take that point, substitute in your function, you get a y value. It's called f of x. Remember, f of x is just this fancy notation for y. Okay, this is a y value. And then Q is x plus delta x. Go up to the function, okay, and then move left. Look at the y value there. Evaluate the function at that point, which is x plus delta x. And you get f of x plus delta x. That's a y value. Okay, we can call f of x right here our first y value, y1, and then our second y value, we can call it y2 if you like, coming back from geometry. So we know the coordinates of Q1 now. We know that it's x plus delta x, comma, f of x plus delta x. Okay? Now, then we go and find the slope of the secant line, and then we learn how to get it infinitely close to P. Okay, so let's take a look at the slope of the secant line. And let's kick in a little bit of Algebra 1. The slope of the secant line is found the same way you found the slope of any line in Algebra 1 and 2. You take the difference to the y's and divide it by the difference to the x's. You take the rise, which is calculated by taking a difference, y2 minus y1, and then you divide it by the run, which is x2 minus x1. This is x2 and this is x1. Okay, so the slope of the secant line, as you guys know, is rise over run, or in other words, y2 minus y1, divided by x2 minus x1 in general. This is our definition of slope. So let's apply that here. So we're going to take the difference of the y values, which is f of x plus delta x minus f of x. So we have f of x plus delta x minus f of x. This is the difference of the y values in the numerator, divided by x plus delta x, the one on the right, minus the one on the left. So you have x plus delta x minus x. That's your slope of the secant line now. Okay? Now let's simplify that a little bit. The numerator stays the same. Alright, but you notice here that the x's cancel out, just giving you delta x. Now what we want is to find the slope of the tangent line. Okay, well that's easy to do, because the slope of the secant line is a good approximation for the slope of the tangent line. All we have to do is move Q1 infinitely close to P. We want to slide it down here and get it infinitely close to P. Well, how do we do that? Well, as Q1 approaches P, that means that delta x right here, this distance, this point's going to go this way, and delta x is going to shrink. Delta x right here is going to approach 0, because if you close Q1 to P, then the distance between x plus delta x and x has to approach 0, which means delta x has to approach 0, which means you've got to take a limit. Okay? So what we want to do is take a limit of this slope here, and this is the key now, and this is going to give us our derivative, which is the slope of the tangent line, f prime of x, which is the slope, okay, or you can say y prime, is going to be equal to, now the limit as delta x approaches 0, this distance that goes to 0, because we're going to slide Q1 to P now, of the slope of the secant line. So f of x plus delta x minus the function, okay, f of x, divided by delta x. We call this the limit definition of the derivative. This is what's called the limit definition of the derivative. And it's what you're going to be using in this entire section to calculate all derivatives. So we need to commit this to memory, all right, because it is the main tool that we're going to use to find all derivatives. It is the main tool that we're going to find all slopes of the functions at any point P, and it's the main tool that we use to calculate or to derive basically all the derivative rules that you're going to be seeing throughout the chapter. It is the foundation of everything we're going to do in this chapter. So when I say state the limit definition, and I'm talking about the limit definition, I'm talking about exactly this. The limit as delta x approaches 0 of f, the function, evaluated x plus delta x, minus the function itself, all divided by delta x, as delta x approaches 0. That's called y prime or f prime, or we can say dy dx. Okay, so you have three ways to name the derivative of function y or function f in this way. Okay, and the only thing you need to do is get used to it. Okay? We find the derivative of f as, well, I just stated it right here. The derivative of f. Okay, we derive all basic differentiation formulas using this definition. All right, so here we go. Turn the page and let's get started on our first example here. Example 1, we need to find the derivative of x squared. F of x equals x squared, or y equals x squared, using the limit definition, because that's all you know right at this moment. Okay, so here we go on our first example of how to find the derivative of y equals x squared. So when it says find the derivative, that means find y prime. What is that equal to? Or you can say f prime of x. What is that equal to? Or you can say dy dx. What is that equal to? When it says find the derivative, that's what I'm saying. Okay? Now, I'm going to write the limit definition of the derivative here. F prime of x is equal to the limit as delta x approaches 0 of the function evaluated at x plus delta x minus the function itself, all divided by delta x. This is your limit definition right here. And since it's new, let's go ahead and keep it on the left side and keep it in our sights at all times. Okay, so let's start. Here we go. F prime of x is going to be equal to the limit as delta x approaches 0 of the function evaluated x plus delta x. So what I need to do is I need to take this right here, and I need to substitute it into our function. That's all it means. Okay, so you got to substitute it in. So let's do that. We're going to take x plus delta x, and we're going to square that, minus the function itself. So we got to subtract the function itself, and that's x squared, all divided by delta x. Now we did this a little bit in the first chapter, but you just didn't know it was dealing with the derivative. And I said take that, substitute in the function, go ahead and square this binomial, and then simplify the expression and take the limit. Okay. Now one other thing I want you guys to do is I want you guys to remember how to square binomial in your head. So recall that in Algebra 1 that a plus b, quantity squared, equals a plus b times a plus b. Well, what does that mean? If you use FOIL, you get a squared plus ab plus ba plus b squared. These two are the same terms, and so you get a squared plus 2ab plus b squared. So what you do is you square, okay, then you multiply the 2 and you double it. That's what the times 2 means, double, and then you square again. So square, multiply, double, square. These are not subtraction signs, these are just dashes. Square the first, then multiply the 2 and double it, square the last. And that's how you square all binomials, just by looking. So get used to that because it happens a lot in this class. Okay? So let's take the limit as delta x approaches 0. And let's expand this binomial here. We're going to square the first term. We're going to multiply the 2, x times delta x, and double it. So plus 2 times x times delta x plus delta x squared minus the function itself, all divided by delta x. And as you can tell, you can't take the limit yet because you can't substitute 0 in for delta x because you can't divide by 0. So the goal in all these problems is to cancel out the delta x and evaluate the derivative. So let's write that down here. The goal in all of these, to evaluate the derivative, you must cancel out the delta x. Okay? So to evaluate the limit here, evaluate the limit, okay, you must cancel out the discontinuity or remove the discontinuity. You must remove the discontinuity, which means, okay, delta x. Okay, you can't substitute in delta x or 0 in for delta x right now because you can't divide by 0. So the goal in all these limit definition problems, when you find the derivative, is to simplify the expression somehow using all your limit techniques, cancel out the delta x so you can evaluate the limit. All right, so what we need to do is simplify the numerator. Okay, so let's do that. Notice that the x squareds cancel out. Okay, so let's keep on going here. So you have the limit as delta x approaches 0. The x squareds cancel out right there. Notice that they have a delta x in common. You're always going to factor that out somehow. So let's do that. Why? Because you want to cancel out with the 1 in the denominator. That's what I mean, remove the discontinuity there. Remove delta x. Remove delta x there. So let's factor out the delta x from this. You get 2x here. And you factor out the delta x from delta x squared. You get delta x. Notice that the delta x cancel, which is what I was talking about earlier here, which is good because now I can evaluate the limit. So I now have the limit as delta x approaches 0 of 2x plus delta x. You substitute your 0 in, and it gives you 2x plus 0, which is 2x. And this becomes your derivative of f, which we call f prime, or you can call it y prime, or third way you can say dy dx. And that's equal to 2x. This is your goal. Okay? And this is your goal. This is the derivative. Later on I'll talk about what the derivative is used for, but right now you just have to learn how to calculate it, okay, using what's called the limit definition. So f prime of x is 2x, y prime is 2x, dy dx is 2x. These are all notations for what's called the derivative of the function y. Okay, so what I'm going to do is I did it for a polynomial, x squared. Now I'm going to do it for a rational function, 1 over x, and then I'll do it for a root function to give you the three basic types of functions that you need to learn how to take the derivative of. So the first one's a polynomial. Now we do for a rational function right here. The three classic cases that you need to get used to, a rational function, okay? And again, the one up top here, the x squared, for this case, we have a polynomial here. So I did it for a polynomial first, which is the easiest case, and then then I'm going to do it for a rational function, and then I'll do it for a root function. Okay, so one more time, let's have the derivative in our sight. So we have y prime is equal to the limit as delta x approaches 0 of f of x plus delta x minus the function itself, all divided by delta x. Notice how you write it down every single time and memorize it. Okay, write it down every single time. Okay, what we need to do is take this here and substitute in our function. In this case, you just substitute in the denominator. So f prime in this case is going to be equal to the limit, and you have to state that. If you don't put the limit notation down, you're not taking the derivative. All right, and it'll be totally wrong. So make sure you write it correctly. You're going to take that and substitute it in, and you're going to have 1 divided by x plus delta x, all right, minus the function itself, all divided by delta x. That's your setup. That's your first initial step. Now, when I combine fractions, I use what's called a three-product rule. So you've seen me do this before, but let me state it again. This helps me combine fractions really fast. Okay, so a divided by b minus c divided by d. All you have to do is multiply here, and multiply here, and then multiply here. That's why I call it three-product rule. And you can combine fractions in either addition or subtraction. So let me go plus minus here. Really, really quickly. A times d, plus or minus whatever it's given, b times c, okay, all divided by b times d. Very, very simple. So in other words, 2/3 minus 1/2 is 2 times 2 or 4, minus 3 times 1, 3, all divided by 3 times 2, 6, equals 1/6. That's just an example. Very simple idea called the three-product rule. And we want to combine the fractions here. Okay, combine fractions and simplify the expression, okay? And simplify. So to combine these fractions, just kick in your three-product rule all the time. So f prime is going to be equal to the limit. Notice how I keep my notation. Some of you guys forget and leave off the limit notation. No good. You only take off the limit notation when you take the limit. All right, so you got to keep it with you because it means something. Okay, so we start with the left product here. So x times 1 is x, and then minus x plus delta x times 1 would be x plus delta x, minus that, of course. So first product, second product, all divided by the third product. So multiply the denominators, and you get x plus delta x times x, all divided by delta x. Okay, so what we want to do is simplify here. So this is equal to the limit, because I haven't taken the limit yet, of this crazy looking fraction here. And what I want to do is understand that I'm dividing by delta x, so I need to multiply by the reciprocal here to simplify things. So I've got x minus delta x. So notice that the x is canceled here because I have to distribute it in. And this just gives me negative delta x. Okay, so I've got negative delta x in the numerator divided by x plus delta x times x. Now I need to take this and I need to multiply it by the reciprocal of this. So instead of dividing it by delta x, I want to multiply, okay, by the reciprocal. Okay, so here we go, times the reciprocal of delta x. That's a very simple thing. I'm just using a little bit of basic mathematics here. So I take the top fraction divided by delta x. That's the same thing as taking the top fraction times the reciprocal of x. The reciprocal of delta x, which is 1 over delta x. Okay? Let me highlight that because that happens a lot. Instead of division, I multiply by the reciprocal right there. That happens a lot. Okay, and then you simplify, okay? Remember, your goal is to cancel out this continuity. I'm going to do it right now. Ooh, look at that. All right, and I get -1 in the numerator. So now I have a simple limit that I can evaluate. Okay, we're going to take the limit of delta x as delta x approaches 0. I did say it correctly. The limit as delta x approaches 0 of -1 divided by, we got x plus delta x times x. All right, these delta x's cancel out earlier. Now I take this and I substitute it in, and I get -1 divided by x plus 0 times x, which gives me -1 over x squared. And so y prime, or f prime of x, or dy dx, is equal to -1 over x squared, and that's my derivative. Okay. Later on, after knowing your derivative rules, you're going to be able to get to from the function right here to the derivative just by looking at it, and you're going to avoid all this. But to develop those rules, you need what's called a limit definition. Otherwise, those rules cannot be developed. All right. But later on, you're going to be able to avoid all this and go from here to here. Our goal, this is our derivative, in basically one step just by looking, because I can just get from there to there just by looking. All right, and you will too. Okay, you just got to take it step by step. All right, let's do it one more time. This time for our third class of functions called the root function. Okay, you need to do it for basic polynomial functions. That was the first example. And then you need to do it for rational functions. That's my second example. And you need to do it for root functions, which is my third example. Okay, so find the derivative, y prime, what does that equal? Okay, f prime, what does that equal? dy dx. Okay, get used to the terminology here. These are all the same thing, meaning that find the derivative of the function given that f of x equals root x. And as I always say, write down the limit definition right here so you can have it in your sights because it's the first time you've seen it. So the limit of, as delta x approaches 0, of f of x plus delta x, got to write it correctly here, delta x minus the function itself divided by delta x. And again, you want to try to remove the delta x so you can evaluate your limit. Okay, so let's take this and let's go for it here. Y prime or f prime, however you want, whatever terminology you want to use, is equal to the limit as delta x approaches 0 of the square root of x plus delta x minus the function itself, root x, all divided by delta x. Again, this is right here. This is f of x plus delta x minus the function. Okay? You just substitute this x plus delta x into the function, subtract the function itself, and divide by delta x, and then kick in some of your limit techniques. Okay, now in this one here, since we're dealing with root functions, you need your technique you learned in the last chapter by using the conjugate. You want to multiply by the conjugate in the form of 1 and use that to help you evaluate your limit. So write small because it's going to take a lot of room. So the square root of x plus delta x minus the function all divided by delta x. I'm going to use the conjugate of the numerator. So just change from minus to plus. So the square root of x plus delta x plus now conjugate. Okay, plus root x in the form of 1, x plus delta x plus root x. This is a form of 1. Okay, so using the numerator as a conjugate in the form of 1, we can multiply these two and simplify the expression and evaluate your limit here and get our derivative. Okay, so here we go. Now recall that a plus b times a minus b, which is what we have here, a minus b times a plus b, is nothing more than a squared minus b squared. So what I'm going to do is I'm going to square both and subtract. And when you square root, you get what's inside. So you get x plus delta x when you square that, minus when you square the root x, you get x, all divided by the denominator, which is delta x times the quantity here. Now you don't want to distribute through the delta x because you want to leave the delta x on the outside, because you're going to try to remove the delta x, because we got to always do that in these limit problems. So what do we have? Okay, well, simplifying a little bit, you notice that the x's cancel, and let me see, and the delta x's cancel, leaving 1 in the numerator. So I've got the limit as delta x approaches 0 of 1 divided by the square root of x plus delta x plus root x. This is root x right here. And I want to substitute in 0 in for delta x. So what do I get? I get 1 divided by root x plus 0 plus root x gives me 1 divided by 2 root x. And there's your derivative, f prime. Okay? That was my goal. So you've seen it me do this a couple different times, or 3 different times so far. I did it for a polynomial, then I did it for a rational function, and then I did it for a root function. Okay, let's take it one step further, and let's do this for a cubic polynomial right here, and evaluate the, not only find the slope of the tangent line, but let's find the tangent line itself. What is it equal to? Y equals, mx plus b as a function. Find the tangent line itself using the slope and using some Algebra 1 techniques. So the very first thing I need to do is find the derivative. Okay, so again, the derivative is equal to the limit as delta x approaches 0 of f of x plus delta x minus the function all divided by delta x. Okay, so let's get started here and let's find the derivative. Y prime is going to be equal to the limit as delta x approaches 0 of x plus delta x, quantity cubed, minus the function itself divided by delta x. So I have to cube this binomial here. So let's get to work here. So I need to understand that x plus delta x squared times x plus delta x is the same thing. Okay? So what I do is I square the binomial and then I multiply it by x plus delta x, and then I simplify my numerator. So write small because there's going to be a lot of multiplication going on here. It's not a hard problem, it's just a lot of tedious Algebra 1. Okay? So what I want to do is work on this first. I want to square this and put it in here. Okay, so I square the first term, then I multiply double, and then I square the last. Okay, I square, multiply, double, square the last. And now I want to multiply the polynomials and then simplify the numerator. So I get the limit as delta x approaches 0 of this monster fraction. So x times x squared, I'm going to distribute through the x 3 times here, gives me x cubed. X times 2x delta x gives me 2x squared delta x. So 2x squared delta x. And x times delta x squared gives me x and then delta x squared. Distributing through the delta x gives me x squared delta x. And then delta x times 2x delta x gives me 2x times delta x squared plus 2x times delta x squared, and then delta x times delta x squared gives me delta x cubed. So delta x cubed, and then minus the function there. And then you're going to simplify these things. I notice that the cubes cancel. That's cool. And then everything contains a delta x. So I'm going to factor it out and cancel it with the denominator. So I've got here the limit as delta x approaches 0. And then I factor out the delta x, and what do I get? I get 2x squared plus x delta x plus x squared plus 2x delta x plus delta x squared, all divided by delta x. And then you simplify, cancel out the discontinuity there, and substitute in 0. Everywhere you see delta x. So I need to have a 0 here, and here, and here. So I get 2x squared plus x squared, and everything else is 0. So I've got 2x squared plus x squared gives me 3x squared, and there is your derivative. Okay? So y prime is equal to 3x squared. There's my derivative. A little bit tougher to do with a cubic polynomial, but hey, we did it. Okay, now I haven't found my tangent line yet. This represents the slope of the tangent line at any point. Okay, this represents the slope of the tangent line at any point. That's the meaning of it, at any point. Okay, so my whole goal, and let's take a look at it here, is to find the slope of the, or find the tangent line itself at 1, 1, where x is 1 and y is 1. So x equals 1 here. So I'm going to substitute 1 in there and get the slope of it. Okay, so here we go. So what I do is I take y prime, evaluate it at 1. And so that's 3 times 1 squared over 3. And this is my slope of the tangent line at x equals 1, or 1, 1. This is my slope. And so what I need to do is just use that into, use that to find the equation of the tangent line. So my general equation that I use for all problems is y minus y1 is equal to m times x minus x1, where this represents your slope. This is called point slope form. Point slope form. And my point is 1, 1, point of tangent C. Point of tangent C given in the problem. Point of tangent C is 1, 1. So this is my x1 and this is my y1. So what do I have? I get y minus 1 equals slope 3 times x minus 1. Again, I just substitute my slope in my x and y ones. I simplify a little bit. I get y minus 1 is equal to 3x minus 3 after you distribute twice. And then I add 1, add 1. What do I get? I get y equals 3x minus 2. And this is my tangent line. And that's my goal of the problem. All right, that's what you're going to be doing. So the derivative right here, the derivative, which is right here, that was our main goal in the beginning, gives us the slope of the tangent line. Okay, this is important. The slope of the tangent line at any point. Okay, and then you evaluate the slope, or the function, the derivative, at that point. So you substitute x in. You get the slope, which is 3. And then you use the point and the slope in point slope form to get your tangent line. And that is your main goal at the end. All right. You can review this, try this on your own. I suggest you practice it a few times, get used to it before you do your homework, and give it a shot. Now there are many places or different, many different cases, or 3 different cases where the limit fails to exist, and we need to explore those cases, or at least, yeah, a couple different cases where the limit or the derivative fails to exist, and we're going to explore that in part 2. I'm going to end this as the end of part 1. I'm going to get to part 2 in a minute and finish the lesson. In the meantime, you can start your derivatives in your homework, and then I'll finish up in part 2.